Howdy. I will wait one more minute and get started. Okay. Hello, everyone. So we've got a short class period today. So I'm going to try and keep this lesson to about 20 minutes. And then at the end of the 20 minutes, we'll just check in the Zoom room and I'll let you guys go. Okay? So let's get started. So this is CHL 29 period 7. We do have office hours today. There's a question. I will be here for office hours. So today's lesson is about calculating the electric field due to a discrete set of charges. Okay. So what does that mean, a discrete set of charges? Well, that means that the individual charges, we can count them. We can say, oh, there's charge 1, there's charge 2, there's charge 3, there's charge 4, etc. If you have an extended blob where there's charge throughout continuously, that would not be a discrete set of charges. Okay, so we have individual point charges all over the place, and we're calculating the electric field due to those. Okay, so there's two equations that we'll use, and you already learned those equation or the equation. It is Coulomb's law. Now, what I said Coulomb's law was, is I said that the electric field due to a single charge is going to be K times the absolute value of Q over R squared. Okay, but if we want to know what is the vector electric field, this is just a scalar, right? So we have to multiply this by some direction vector. Okay, and it's a unit direction vector. So basically, now if you have a unit vector has length 1. So we take this unit vector and we multiply it by this scalar. And what that's going to do is it's going to make the magnitude of this equal to KQ over R squared. Okay? If you take a unit vector and you multiply it by the number 5, that's going to increase its length to 5. And so the magnitude will now be 5. If you take a unit vector and you multiply it by 11, you are going to now make its length 11. If you take a unit vector and you multiply it by 97, its length will now be 97 after that multiplication. Okay? So basically, this has the direction, and this part has the magnitude. Okay? Now, how do we get the electric field, the total electric field due to all the charges? Well, what we do is we simply sum up the electric fields of each of the individual single charges. Now, if it was a continuous distribution of charge, this would have to be some kind of an integral. Okay? So these are our main equations today. All right, so we're going to do an example. And this is just going to review how do you find a unit vector, okay? So what if I have 2 points and this is the point A and this is the point B. Point A is at coordinates 0, 10. Point B is at coordinates 5, 1. All right? And what we want to do is we want to find the unit vector that extends from A to B. All right? Which I will call RAB hat. So the first thing we want to notice is that, well, this distance right here, because A has y-coordinate 10 and B has y-coordinate 1, if we want to go from A to B, we have to go down 9. Okay? And because A has x-coordinate 0 and B has x-coordinate 5, we have to go over 5. Okay? So what if I were to draw the full vector? The full vector from A to B. So I'll call that RAB, but instead of having a hat, it just has an arrow. Okay? Well, that vector goes down 9 and it goes over 5. So that means that the vector that extends from A to B goes over 5 and it goes down, so there's a minus sign, 9. Okay? So that means that the magnitude of the vector from A to B is going to be square root of 5 squared plus -9 quantity squared, which I'm doing the same example as the last class period, so which is equal to 10.3. Okay, so what happens if we take a vector and we divide it by its magnitude? So if a vector has a length 5 and we divide it by 5, now it has a length of 1. So by taking a vector and dividing by its magnitude, we make it a unit vector. We preserve its direction, but we shorten it so that its length is now just 1. Okay? So the unit vector from A to B, all right, so we have to divide to just make it a unit vector that goes from A to B, is going to be the full vector from A to B divided by that full vector's magnitude. So the full vector from A to B is 5 I hat minus 9 j hat. And we want to divide that by the magnitude, which is 10.3. All right. So remember the division distributes, distributive property of division. So if I do that division, and again I have this written down from last class period, is 5 divided by 10.3 is 0.49 I hat. -9 divided by 10.3 is 0.87 j hat. So this would be our unit vector. So we're going to have to do that kind of a calculation when we calculate the electric field because it's a magnitude times a unit vector. Okay, so that's why we have to do that kind of calculation. So we can just double check that this is a unit vector by doing the magnitude. So do the Pythagorean theorem on this. So the magnitude of that is going to be 0.49 squared plus 0.87 squared square root of that. And if you work that out, it is equal to 0.998, which is approximately 1. Why isn't it exactly 1? It's because I did some rounding at various stages in that calculation. Okay. So now let's do an example of actual electric field, calculating an electric field. We want to find the electric field of find the electric field for a dipole. So if you've ever heard water is a polar molecule, we could model water as a dipole. Because of the shape of the water molecule and the difference in electronegativity between the oxygen and the hydrogen, the oxygen pulls the electrons to that side of the molecule, leaving a lack of electrons on the other side so that it has a net positive charge. So a dipole, what a dipole is, it means you have a positive charge and an equal amount of negative charge that are side by side, separated by some distance. So we'll say that this positive charge is at coordinates negative d, 0. The negative charge is at coordinates positive d, 0. So here's the origin right here, and halfway in between them. This distance right here is d. This distance right here is d. Okay? And then we have a point P up here. This is the point P. And it is a distance y above the origin. So it's at 0, y. All right? So what we want to do is we want to find the electric field at point P due to those two charges. Okay? Now, because there's just two charges, it's going to be equal to the electric field due to the positive charge plus the electric field due to the negative charge. All right? Now, this positive charge creates an electric field that goes away from it. So if you're at point P and you want to run away from that positive charge, you're going to go up in this direction. Okay? So that is E plus. Negative charge creates an electric field that points towards it. So if you're at point P and you want to run towards that negative Q, you're going to run in that direction. So there's E negative. Okay? All right. So let's go ahead and find the direction vector for the positive charge and the direction vector for the negative charge. All right. So for the positive charge, there's a question in the chat. Let me read this. This is like when we found the magnitude of gravity with point mass. Yeah, it's very similar. Very, very similar. In fact, the math is identical. The interpretation is different because it's electric fields instead of gravitational fields. So if we look at let's find the direction vector for E plus. We can see that this line is parallel to that line. So I'm going to use this line and create the electric field that's parallel to that, or the unit vector that's parallel to that line. I can see that this line, it goes over D and up Y. So this direction vector is going to point in the same direction as D I hat plus Y j hat. And then I have to take that. This doesn't have a length of 0, or a length of 1, excuse me. So I have to divide by its length. Okay, so doing the Pythagorean theorem on that means that the length is square root of d squared plus y squared. Okay, so that is the unit vector that points in that direction. The unit vector from the negative charge is, I'm going to use the fact that that this unit vector is going to be parallel to that line, which I can see goes down y and over d. So that points along di minus yj. And again, to make it a unit vector, I have to divide by the magnitude, which is going to be square root of d squared plus y squared. Okay, so now that's going to allow us to get the electric fields, E plus and E minus. So to get E plus, the magnitude is K times the absolute value of plus Q, which is just Q, over this distance squared. This is C. So by the Pythagorean theorem, C squared equals D squared plus Y squared. Okay. Nice thing about Coulomb's law is that because it has R squared, you don't need to take the square root at the end, right? When you do Pythagorean theorem. So this is just going to be D squared plus Y squared. And then I multiply it by the direction vector, which is d I hat plus y j hat over square root of d squared plus y squared. So that is the electric field due to that positive charge. For the negative charge, I have K times the absolute value of negative Q, which is just Q, over this distance squared. Now this is basically an isosceles triangle, so that means that because it's an isosceles triangle, that means that this distance is the same. And then we multiply that by its direction vector, which is d I hat minus y j hat over square root of d squared plus y squared. So hopefully everyone is seeing that this should be d squared plus negative y quantity squared, but negative squared is plus 1. Okay. So now to find the total electric field, I have to add those together. That's going to give me the electric field at point P. And notice how I have these expressions are identical, with the exception of this being plus y and this being minus y. So when I add those together, these two are going to cancel out. These two terms are identical, so they're going to add and make double. Okay, so I'm going to have kq over d squared plus y squared times 2d I hat over square root of d squared plus y squared. All right, and just simplifying that a little bit more, d squared plus y squared times square root of d squared plus y squared is going to be d squared plus y squared to the 3/2. power. And then on the numerator, I have 2kqd times the direction I have. So this is our answer. Okay. So I'm going to try and do one more example really quickly, probably too quickly, for you guys to understand it completely, but I'm just going to squeeze it in there. So what if I have a square of charges and they're all identical, except for the signs might be different. Plus q, minus q, minus q. Okay, and it's a square of side length A. And I want to find what is the magnitude of the electric field at the center. So here's the center right here. All right, so one of the things we want to notice is that the center of a square is the same distance from each of its corners. So what is that distance? Okay, well, if you have a square that is, if you have a square that has a side length A, then the diagonal of that square, by the Pythagorean theorem, is going to be square root of 2a. But we can see that each corner is half a diagonal from the center. So this distance right here is square root of 2a. It's half a diagonal, so over 2 equals a over root 2. Okay? So if I want to know what is the magnitude of the electric field due to a single charge, it's going to be kq over a over root 2 quantity squared. And that's going to be 2kq over a squared. Okay? Now let's think about how do these combine? Well, this charge creates an electric field that is that way. This negative charge creates an electric field that is towards it and is that way. This positive charge creates an electric field away from it that is that way. And this negative charge creates an electric field that is towards it and is that way. All four of these electric fields are of the same size, okay? Because they're all the same magnitude of charge and they're all the same distance from the center. So if we think about it, these two are going to combine and double the length. So these two will combine to make an electric field that goes that way of size 4kq over a squared. And then these two combine to make an electric field that's double the size of an individual one. So these two also make 4kq over a squared. Okay, and this is a right angle between them. So we want to add these two vectors together. So we do the parallelogram rule. And this is going to be the total electric field pointing downward. And this is just, again, this is a square. This parallelogram is a square. So this is the distance across the diagonal of a square. So it's going to be a side times square root of 2. So that means that our electric field is going to be square root of 2 times 4 kq over a squared. So that's our answer. So I know that was a bit quick, but I want to make sure we have time to check in the Zoom room. So that is my lesson for today. I'll see you in the Zoom room.